Our next topic for chapter 11 is called mechanism of dissolving. What that means is we want to look at what actually happens to a solute when it dissolves into a solvent. So we've already kind of hinted at if we have a covalent compound. So this would be a compound where covalent bonds are holding an individual molecule together. And so in a solid, that's just a bunch of molecules held together by intermolecular forces. And when those solids or liquids dissolve, they just freely float as molecules. So this is the idea of that we want, say this is sugar. When the sugar dissolves in water, it separates out and becomes an independent sugar molecule. And it's floating around, as if it was a liquid, freely moving, freely flowing over other molecules. Importantly, the only thing that's broken is intermolecular forces. So say sugar is held together by hydrogen bonds. So all those hydrogen bonds are going to be broken between the sugar molecules, but importantly, no covalent bonds are broken. So it's just the whole molecule. So in terms of the molecular formula, we expect to see it's just the same molecular formula, and the only thing we change is that AQ. If we have ionic compounds, the dissolving leads to breaking of the ionic bonds. So when ionic compounds dissolve, the ions separate from each other. In an ionic solid, say over here in the salt, we have all sorts of cations and anions packed together that are being held together by the attractions of the opposite charges. Okay, so it's not discrete molecules anymore. It's just kind of this infinite array, this crystal of ions. And so when they dissolve, the water molecules come in and will break all of these ionic bonds. And then we can see you'd have, say, your anions and your cations independently moving around from each other. So in the chemical formula, we would say NaAQ, Na plus AQ, and then the Cl minus AQ. Importantly, we do denote that they have charges. We still say AQ because they're still dissolved in water, but we write them separately because they are independent objects moving around, and they have their charges still because they are ions. So let's look at an example. Let's complete each of the following chemical equations. I have KBr solid dissolving in water, Na2S dissolving in water, NH4Cl dissolving in water, and CH3Cl dissolving in water. So, okay, so when we want to come up with the chemical equations for dissolving, which we can see we have all these solids, and then it's H over the arrow. That means we're looking at dissolving. And the first question is always going to be, is this thing ionic or covalent? Because we know that there's two different mechanisms that happens when we dissolve for those different cases. And so just as a refresher, when we want to determine whether or not something is ionic or covalent, we want to look for are there ions. And one of the giveaways is if the first element is a metal and the second element is a non-metal, because metals tend to form cations and not form covalent bonds. So when we have KBr, K over here is a metal, Br over here is a non-metal, meaning that K is the cation and Br is going to be the anion. If we have two non-metals, that's a sign that we have a covalent compound. But K is a metal, so that means this is an ionic compound. We know that ionic compounds are going to break apart. So in this case, I just have K and Br. Those are two different atoms. And so we know those are going to separate out. And so when we want to write it, when this actually dissolves, what'll happen is we get K, which will be aqueous, and Br, which will be aqueous. So we do want to note that aqueous needs to change. The phase needs to reflect the fact that it has dissolved. The other important step is that we need to include the charges on these ions. So if we look at K, we know as a metal that it's going to form a cation, which means it will be positive. So exactly how positive will it be? Well, it's in column 1, which means column 1A, which means it will be +1. We know it's a +1, plus 2. On the other side of the periodic table, bromine is in the halogens. We know the noble gases don't form ions. We know that this column, the halogens, are one away, so it's -1, -2, -3, -4. It doesn't go all the way down in these columns, but we know the non-metals in those columns are going to tend to form -1, -2, -3, -4, because they're gaining electrons to look like a noble gas. So hopefully you have a periodic table. You'll note there's an additional resources folder on Blackboard where there's a handy-dandy periodic table for you to use. This periodic table, if you would like it, you can also use your own. I highly encourage you to get a periodic table to use. So that's going to be K plus, and that's going to be Br minus. So when potassium bromide dissolves, it's potassium ions and bromide ions. It is worth noting that oftentimes when we write this, we would still say like KBrAQ. So we're going to talk about these salts and talk about them as being dissolved. And the thing we have to know, the one thing we want to remember is that when we write this, when we write that we have a dissolved salt, that really it is two independent ions that are floating around in solution. It is not just KBr as like a combo floating around. It's K floating around and bromide floating around by themselves. That's why they're added together. They're not linked together. The plus sign indicates that they are separate species. So Na2S is next. Sodium is right below potassium on the periodic table. Right above, sorry, potassium periodic table. So this is definitely ionic again. That's a metal. So that's going to break right there. So it's going to separate out. And we know we're going to see Na AQ plus S AQ. And so we need to get our charges. We said Na is in group 1A. It's right above potassium, so it is also plus. Sulfur is right below oxygen, so this was -1, -2 in group 6A. So sodium is a +1 cation, sulfide is a -2 anion. And so we've got our ions, we've got them dissolved, and we have their charges. The last thing we need to account for is balancing our equation. So I got 2 sodiums right there. It needs to be 2 in front right there. That 2 needs to be out front. What we do not want to write is this. That is no good. This, when we write it like that, when you write the script, you imply that those atoms are linked together in like a molecule. Instead, the 2 goes out front to indicate that those 2 ions are the same type of ion, but they're floating around independent of each other. All of the ions separate out and become independent objects in solution. Because sodium cations are just single atoms, each single atom breaks apart. NH4Cl. This is a tricky one because N is right here. We think, hey, that's a nonmetal. H is over there, but that's a tricky one. That's a nonmetal. So we think, hey, this is probably covalent. Chlorine's also a nonmetal. But NH4 is called ammonium. And ammonium is a polyatomic cation. And so our rules for determining ionic and covalent. Ionic, if it starts with a metal and ends with a nonmetal, that's ionic. Or if it starts with NH4. NH4 is the ammonium cation, NH4 plus, coming out right there. That is a polyatomic cation right there. So the ionic bonds still break when you dissolve, and they separate out. We have the NH4 plus and the chloride that they separate out. You do not separate the N, H, and 4. That is collectively one polyatomic ion. Polyatomic ions are molecules. right? They are held together by covalent bonds, so you don't separate those. So we want to be mindful of what the polyatomics are. On Blackboard, under additional resources, there's a table of polyatomics that I'd recommend you use. You know, you're going to pick up, you're going to kind of memorize some of them, especially the ones we use a lot as we move into acids and bases and other reactions. But you can always use that as a reference, what the polyatomics are, what their formulas are, what their charges are. We want to recognize that NH4 is plus, right? We can figure out chloride is minus because it's a halogen. It's right next to the noble gases, but not quite there. We can figure out atomic charges, but ammonium, we either need to look it up or just know that NH4 is NH4 plus. Finally, CH3Cl, carbon, nonmetal, hydrogen, nonmetal, chlorine, nonmetal. No fancy polyatomics here. This thing is covalent or molecular. They're going to form molecules, and those molecules do not break apart. So it just becomes CH3Cl, AQ. So for covalent compounds, we do not break them apart. They stay together. You just change the phase to AQ, reflecting the fact that the molecules are now separated from each other, that were linked together in the solid. So we always want to figure out, is this thing ionic? Is it covalent? And be able to work from there. We know we're going to separate out our ions. We're going to change the sign to AQ, change the charge. We can figure that out from the periodic table for atomic ions. And then for polyatomics, we want to look those up. Covalent, they stay the same. Of course, we do want to be mindful when we're writing ionic compounds. We oftentimes will see this, the same kind of setup as you would for a covalent compound to indicate, hey, this is an ionic compound that's dissolved in water. We just want to be mindful that when we write that, we really mean those two are together, or that they're separated apart. All the ions are all separated apart and free floating in that solution. Since the different types of compounds dissolve differently, they also lead to different types of solutions with different properties. So one of the first distinctions of a type of solution that we could have is we could have electrolyte solutions or non-electrolyte solutions. And the distinction is that electrolyte solutions contain ions, non-electrolyte solutions don't contain ions. So electrolyte solutions are formed when you dissolve an ionic compound. Non-electrolyte solutions always correspond to dissolving a covalent compound. Okay? In an electrolyte solution, there are ions present. We'll see there are some other exotic ways that you can produce ions, not from potentially a reaction that creates ions in water. But for now, we're going to say if an ionic compound dissolves, that's an electrolyte solution. Covalent compound dissolves, that's a non-electrolyte solution. And so the reason this name electrolyte, that part of the word electro, really does correspond to electricity. So what happens is when you have pure water, it doesn't really conduct electricity at all. When you have ions that are separate from each other, you now have some charged particles floating around in the solution, and that enables the flow of electrons through the water. Right? That's conducting electricity, is moving electrons around the water. So if you have, so you think about like you shouldn't swim because in like a lightning storm because you'd get you get shocked by lightning. That's because the water that you're swimming in has a lot of salt in it. It's very hard to get pure water. You'll note when we use like deionized water in the lab, it's not pools worth of deionized water. It's, small squirt bottles. Bigger pools like that are going to certainly have salt in them of some sort. Your body is covered in salt, so when you get in there, you'd affect it. And so there is going to be conduction. The other important thing to know is lightning is a really a lot of potential. It's going to flow through whatever it wants to flow through. And so, but if you have deionized water and it's not going to really conduct electricity. You put sugar in it, it's still not going to conduct electricity. Participation 121, question 1. How many dissolved ions are present in solution for each 1 formula unit
for each of the following compounds. So I have 4 compounds. It's LiF, that's lithium fluoride, Al2CO33, that's aluminum carbonate, BaSO4, that's barium sulfate, and NH4NO3, ammonium nitrate. This is the first question on participation 121, due Friday, January 21st at 11:55 p.m. over on Blackboard. Link to the assignment is right below the links to these videos. Again, how many dissolved ions are present in solution for each one formula unit for each of the following compounds? So I'm looking for a number. It's lithium fluoride, aluminum carbonate, barium sulfate, and ammonium nitrate. Got our first participation question in this video. Just getting started though. Got a couple more videos to go. See you in the next one.